quickly, this is the airlock section of our chamber. If we want to do a long duration test with astronauts for like a year or 2 years, we can't really put crews in there for a year at a time. So what we'll do is we'll send a crew in for maybe 30, 60, 90 days, and then what we'll do is, using this airlock, you close this door, bring the crew out, close that door, equalize the pressure in here to the outside, and then the crew can go out and 3 more or 6 more people can come in, and we never break the seal inside the chamber. We can keep running our systems, our life support systems. We want to run them until they fail. Figure out why they fail, and then fix that, and then run them again until they fail. These systems need to be reliable for very, very long duration missions in deep space. So this airlock system allows us to keep running these tests without actually losing our atmosphere or our seal inside the main chamber. So let's go ahead inside here. We're trying to demonstrate our life support systems. We're developing new technology life support systems, and if you stop them or shut them down, it's challenging to reset. You want to get them into a steady state mode where they run at that environment without any change. So this is a 3-level chamber. Back in the 60s, when it was originally built to support the Gemini program, it was only 2 levels. And when Skylab started testing back in the mid-70s, we added the 3rd deck on top. Skylab crews spent 56 days inside this chamber at 70% oxygen and 5 psi. Back in the late 90s, we did 3 tests in this chamber with 4 crew members, men and women mixed crews, for 30 days, 60 days, and 91 days without stepping foot outside. I mean, everything was inside here. That was run in a regular, normal atmosphere environment for those tests, so it was like the air that we're breathing now. But for the future testing that we're hoping to build up for in the next few months, we actually want to test at this new atmosphere, that sweet spot in the curve that I pointed to out there, 8 pounds per square inch and 32% oxygen, is what we think is kind of our compromised atmosphere for a deep space mission, so that astronauts can quickly and easily get into their spacesuits and go out and do EVA or spacewalks essentially every day, with very little of this what we call pre-breathe time. If you don't breathe 100% oxygen before you go outside and get into that spacesuit, the nitrogen bubbles out of your blood, can cause decompression sickness to the lungs, and severe injury if it's a bad case. And we can't take that chance. The human body is really one of the weaker links in the chain, if you will, for deep space. I don't mean to be flippant about it, but it's really important that we preserve our astronauts' health and keep them safe so they can perform productively on these long duration missions in space. Does that make sense? So this chamber is a very unique facility that we use. I know it doesn't look quite full out right now because we've got it all stripped down, but we had it in vacuum just a couple of weeks ago, a very hard vacuum, and it was tight. I mean, it was seals, the doors were on, everything was still up tight. Even though it's an old facility, it still works extremely well. And we're looking forward to building it up with crew quarters and a galley and a kitchen and the whole 9 yards that we need to support crews for extended duration testing. Any questions? I realize I'm talking about a minute here, but we don't have much time.
I just realized it's 3 levels. I didn't know that either.
Yeah, there's 3 levels, and the ship's ladder goes up. I'm sorry we're not allowed, for safety reasons, I'm not allowed to take you. We don't have much time either.
No,
we're not allowed to take you up there, but it looks a whole lot like this on the second level. The ceilings aren't quite as high on number 2 and number 3, so this is the highest ceiling down here. And this is generally where we keep all the major life support systems, the bathroom, the kitchen facilities, things like that. It's probably a couple inches thick. It's pretty stout. Partially because it was built back in the 60s, we did things differently back then. We had very, very generous safety margins. We've actually had one of our co-op students here working for us recently who came in here and meticulously with laser measuring tools measured everything, because all the drawings on this facility are so old. They were done on a board, with a T-square and a triangle. You guys probably don't know what that is. It's all CAD now. But we have them come in here and measure the heck out of everything and convert it all to a digital CAD model, Pro E. But now we've got a complete 3D model of this chamber with all the fire suppression, electrical, lighting, everything we need for building up our next generation of tests. Questions? Anybody? Does that make sense?
Yeah,
Oh,
you can
yeah,
see
there are. It's actually these lights. We got them shining through the windows to give us some light in here. There's actually a small equipment here, like that little cylinder right over there by that cabinet. Back when we did the 1 atmosphere testing, we actually passed their mail and things like that through acid trash out. But when we do what we call a closed loop system, we won't use an airlock like that. We need to be able to recycle the water, the air, even the trash. We come up with trash compactor systems. We just literally recycle everything because that's what we're going to have to do on a long duration mission.
Is there a place where they mark off the days on the wall?
I imagine I do have a calendar of some sort, yeah. But this is really, really vitally important. Our NASA program is kind of at a crossroads right now. We don't have a specific program or mission or goal, so we're working really hard to develop the technologies right now so that when we do get direction, go to the moon, go to Mars, wherever we're going to go, we'll have the technology ready and we can actually put it together and build a deep space habitat or a vehicle to take us there. I think your next stop, you're going to go over to building 220, you're going to meet Colonel Al Drew, who's an astronaut. He's going to show you what's called the Habitat Demonstration Unit, and it's kind of a mock-up of what we call the deep space habitat. And once they finish testing the next month or two with that HDU that you're going to see in a few minutes, we're going to strip that down, bring a lot of that equipment over here, build it up inside this chamber, and then we can really close the door and do some very realistic testing at these reduced pressure and rich oxygen environments. The ones we're going to see, it's not sealed. It's like trying to air condition your house with the doors and windows open. But that's okay. It's a model. It's the first step in the chain to get an idea of what works and what we need to build up. The next step is to bring it over here and do it at a realistic environment so that we know that systems don't overheat. At a reduced pressure, something we learned on the shuttle, we have like a computer with a fan in it, and you're operating at 10 psi. There's not much air to push around, and the fan doesn't work effectively. The computer starts to overheat, and experiments get disrupted. So there's a lot of things we have to do to adjust the environment for the crew, for the equipment, and everything on board to make it an effective mission for such a long duration mission to Mars. And it has to be robust, it has to be strong. It really is a failure is not an option scenario. I always tell people on the space station, you're a couple hours from home. If you have an emergency or a fire, you jump into Soyuz, you're back on the ground in a couple of hours. If you go to the moon, you're about 3.5 days from home. You can turn around and come back, kind of like the Apollo 13 guys did. But when you're going to Mars or somewhere else in deep space, you're all in. Okay, you're committed, and there's no turning around and coming back in a quick turnaround mode. So these systems have to work, they have to be robust, and that's what we're trying to do here now. So I'm sorry I'm talking a blue streak. I hope that makes sense. Any other questions? I know we don't have much time.
So the deep space habitat is there for Mars or an asteroid, right?
Right. We're basically trying to develop the technology right now to go to either destination. The ultimate goal is Mars. The question is, will we go to an asteroid first or go to the moon first? But we need that stepping stone to get us to Mars. Because if I had a truckload of money today, I would tell you we don't have the technology to do it today. We've got to do the kind of testing that we do in this facility and many other facilities, develop that technology, get us ready so that we can ultimately make that next big step. Make sense? All right, well, I guess if we don't have any more questions, maybe we should make another Heather. Let's make our way back outside. Thanks for coming.
Thank you.
You're welcome.
Appreciate it.
Yeah, no problem.
I want to.
Oh, yeah, okay.
Ben?
Yeah.
Pretty cool.
Could be a fun day at work, inside the chamber, for 30 days.
What day? Maybe not the 30th.
Well, we would, yeah, there's no, sound event or anything. The walls would probably be. Otherwise.